Hello everyone, welcome to Unit 17 of online course on probability distributions. The last two modules we have discussed some numerical examples related with the binomial distribution. In this module also, we are considering some problems associated with the binomial distribution. Let us consider the first problem. If the probability of success is 0.01, how many trials are required so that the probability of at least one success is greater than 1 divided by 2? So, this is a question associated with the binomial distribution or the application of binomial distribution, by which we are finding the number of trials required to satisfy the probability of at least one success is greater than 1 by 2. So, here we consider, suppose x is a binomial random variable, let x is a binomial random variable, then the probability mass function of this random variable is probability of x is equal to x is ncx p power x q power n minus x, where x is equal to 0, 1, 2, etc. up to n, and p plus q is equal to 1. So, this is the probability mass function of binomial random variable. The question is actually, what is the number of trials required, or how many trials are required so that the probability of at least one success is greater than 1 by 2. That is, we had to find, so we had to find the number of trials required. So, the question is to find n such that the probability of at least one success greater or equal to 1 is greater than 1 by 2. So, probability of at least one success is greater than 1 by 2. That statement is written like this. So, we have to find number of trials n in order to satisfy probability of x greater or equal to 1 is greater than 1 by 2. So, what is probability of x greater or equal to 1? It is actually 1 minus probability of x is equal to 0 is greater than 1 by 2. By considering the complement part of x greater or equal to 1, we know x is a random variable having the values 0, 1, 2, etc. up to n. So, x greater or equal to 1 means this part. So, the complement of that is x is equal to 0. So, 1 minus probability of x is equal to 0 is greater than 1 by 2. And what is 1 minus probability of x is equal to 0? Probability of x is equal to 0 by the binomial probability mass function, we know it is equal to q power n. Probability of x is equal to 0 is q power n. So, this is 1 minus q power n is greater than 1 by 2. So, we have actually the question is to find n in such a way that 1 minus q power n is greater than 1 by 2. And you are given that probability of getting success of that experiment is 0.01. This is given to you. The question, you are given that probability of getting success is equal to 0.01. So that is Q is equal to our 1 minus P, that is equal to 0.99. So this is our Q. So if it is 1 minus 0.99 power n is greater than 1 by 2. So from this, we had to find the value of n, and that is only a mathematical problem. How to find the value of n by solving this equation, this inequality. That is, this is actually, this implies 0.99 power n is less than 1 by 2 by this, and that is n logarithm of 0.99 is less than minus log 2. Earlier we have the equation, inequality 0.99 power n is less than 1 by 2. By taking logarithm, this is n logarithm of 0.999 is less than logarithm of 1 by 2, that is actually logarithm of minus logarithm of 2. So this is the problem. And find the value of n logarithm of 0.99 and logarithm of 2. So actually we have the value, logarithm of 2 is 0.3010 and logarithm of 0.99 is bar 1.9956, that is actually minus 0.0044. So on the basis of this, we have n 0.0044 is less than, this is minus minus 0.3010, because see, logarithm of 0.99 is equal to 1.9956, or that is equal to this one, and logarithm of this one. Okay. So that is the value. That means n greater than 0.3010 divided by 0.0044, and that is approximately equal to. So that means n is, whenever n is greater than this number, our criteria, our probability is satisfied. That is the probability of, actually the problem is, the probability of at least one success is greater than 1 by 2. That criteria is satisfied whenever we are performing the random experiment, that is Bernoulli trials, at least for 225 times. So this is the way we are calculating the value of at least the value of number of trials n. This set in order to get the statement, the probability that at least one success is greater than 1 by 2. And another problem here we are considering, this is a practical situation, we are applying the binomial distribution. According to a World Bank report, only 9% of the population of Uganda had access to electricity as of 2009. It is a World Bank report during 2009. 9% of the population has the access of electricity. Suppose we randomly sample 150 people in Uganda and let x be the number of people who have the access to electricity, what is the probability distribution for x? So, this is a question where we are applying binomial distribution. That is, suppose x is you consider as a number of people who have the access to electricity. Okay? And if it is, what is the probability distribution for x? See, here we have the Bernoulli trial. Why? Because we have two options, access to electricity or not access to electricity. So, success or failure. And you are given that 9% of the population had access to electricity. So, 9% of the population had access to electricity means what? Probability of getting, if access to electricity is defined as our success, probability of getting success is 9%, that is 0.09. So, actually here suppose x is a number of people having the suppose we define x as the number of people with access of electricity and p is the probability 9% of the population. So, that means 0.09 is the population. And so, what is the probability distribution of x? That is probability of x is equal to x. We are sampled 150 people from the population. So, probability of x is equal to x is 150 Cx p power x. P power x means either you can write 9 by 100 power x and q power x. Q power means 1 minus 9 by 100, that is this. So, these are some situations where we are applying binomial distribution. So, this is a problem with respect to a population, and that population have either have the access of electricity or not access of electricity. And suppose from the population have the 9% of the population have the access of electricity, we know the proportion of population have the with the access of electricity, that is 9%. That means probability of success is known to us. And suppose we are selecting a 150 people from that population, what is the probability distribution of x? The probability distribution is probability of x is equal to x is equal to 150 Cx, 9 divided by 100 power x, 91 divided by 100 power 150 minus x. So, that is this, in this type of situations we can apply the binomial distribution for finding probability values corresponding to. Suppose the mean number, suppose the question is regarding mean number. What is the mean number? Mean, the mean of that population, expectation of x, that is equal to NP, you can find, that is 150 into 9 by 100. Suppose the question is about variance, you can find variance of x is equal to NPQ. You can substitute the value NPQ, that is 150 into 9 by 100 into 91 divided by 100. And related probability values, suppose the question is with respect to finding the probability of other events, you can find, because we know the probability mass function of the random variable. So, a situation where we are applying binomial probability mass function, and on the basis of binomial probability mass function, we are finding probabilities, or we are finding the mean, or we are finding the standard deviation, etc., or variance of the population, etc. Okay. And another question that is a theoretical one, that is a numerical, not a numerical problem. Suppose x is a binomial random variable, what is the distribution of y is equal to n minus x? A simple question, a simple characterization property of the binomial random variable. That is, you are given x is a binomial random variable. X is a binomial random variable. And the problem is, suppose we define a new random variable y that is equal to n minus x. Suppose, what is the probability mass function of x, y? The question is, can you find the probability mass function of y if x is a binomial random variable with the parameters n and p? Very simple to obtain the probability mass function of y, because see, if x is a binomial random variable, we can write probability of x is equal to x, the probability mass function, as ncx p power x q power n minus x. Of course, x is equal to 0, 1, 2, etc. up to n, and p plus q is equal to 1. So, this is our probability mass function of x. And what is a new random variable is defined, y is equal to n minus x. Y is equal to n minus x. Consider the probability mass function of y is equal to n minus x. That is, you consider probability of y is equal to some y. You consider this probability of y is equal to y, and that is equal to probability of, what is y? You just replace y, that is n minus x is equal to y. And that is probability of n minus x is equal to y means probability of n minus, we have the last step, n minus x is equal to y. Or that is probability of x is equal to n minus y. That way we can write probability of x is equal to n minus y. That is equal to probability of x is equal to n minus y means nc x. This is nc n minus y p power x, that is n minus y here, and q power n minus x, that is n minus y. That is because we know the probability of x is equal to x is equal to ncx p power x q power n minus x. This is the probability mass function of the binomial random variable. In this expression, you just replace small x by n minus y. So, nc n minus y, p power n minus y, q power n minus y. This is equal to nc n minus y is same as ncy. You know that. nc n minus y is same as ncy. And p power n minus y, q power n minus y means y. So, from this expression, our conclusion is our random variable y is a binomial random variable with parameters n, and this is actually p power y, q power n minus y form. So, here instead of q we have, p, we have value q. So, that is y is a binomial random variable with parameter n and 1 minus p. So, remember, this is the result we have. So, whenever we have x is a binomial random variable with parameter n and p, so x is a binomial random variable with parameter n and p, and suppose we defined y as n minus x, then y is a binomial with a parameter n and 1 minus p. So, this is a result regarding the distribution, regarding the characterization of y, where y is equal to n minus x. So, this is a problem or this is a characterization property of the binomial random variable. That is, x is a binomial random variable with parameter n and p, then y that is equal to n minus x is a binomial random variable with parameter n and 1 minus p. Okay. You consider another problem. So this is a problem actually that is with regard to expected frequencies using the binomial distribution. Suppose in some practical situation, the observed frequencies are, we have observed frequencies, and suppose we are not performing an experiment, and on the basis of the character of the random experiment, can you predict or can you expect, can you say the expected values of the frequencies of certain events? Once again, on the basis of certain character of the random experiment, we are trying to find the expected values, expected frequencies of certain events. So this is an example. You have out of 2000 families with 4 children each, how many would you expect to have at least one boy? Another event, at least 2 boys. Another event, 1 or 2 girls or no girls. So like events. That is, we have a situation that is 2000 families are there, and all those families have with 4 children. If it is so, out of these 2000 families, can you give the expected value of families with at least one boy? And this is a problem we are actually related with finding the expected frequencies. See, what is the situation here? The situation is here, you have a family with 4 children, family with 4 children, okay? And it may be male and female. Okay, and P, let it be equally likely, that is 1 by 2, and so Q is also 1 by 2. And suppose X is the number of boys or number of male child. So that means it may be 0, 1, 2, 3, 4. Okay. So for children family we have X is the number of male child, and it may be 0, 1, 2, 3, 4 values, and P is equal to 1 by 2. So if it is, the question is actually, out of 2000 families, out of such families, families with 4 children, suppose we have 2000, how many of this have, the question is, at least one boy. The question is about at least one boy. How many of 2000 families have at least one boy? How do you find this problem? How do you find the value? At least one boy. So this is our problem. How many of 2000 families, among the 2000 families, at least one boy? So to find this, what we are doing, we find the corresponding probability first. That is at least one boy. At least one boy means X greater or equal to 1. Earlier we defined X is the number of male child or boy. So x how greater or equal to 1, at least one boy means x greater or equal to 1. How do you find this? This is equal to, we have n is equal to 4 and p is equal to 1 by 2. So x greater or equal to 1 means you take the complement, 1 minus probability of x is equal to 0, or that is 1 minus probability of x is equal to 0 is cube power n, that is 1 minus 1 by 2 is our q, and n is equal to 4. So 1 minus 1 by 2 power 4 is the value, that is 1 minus 1 by 16 or 15 divided by 16. So probability of at least one boy is 1 minus 1 by 2 power 4, or on simplification we will get 15 divided by 16. Now the question is, out of this 2000 families, how many of them have at least one boy? That is, we need this expected frequency, that is our expected frequency is probability n into probability of x greater or equal to 1. So that is 2000 into, earlier we calculated this as 15 divided by 16. So 15 divided by 16, 2000 into 15 divided by 16 is the value of the expected number of families having at least one boy, and that is equal to, this is simplified, we'll have 18. So out of 2000 families, we can expect 1875 families have at least one boy. Similarly, you can find the expected frequency of other events. Other events, the other event is 2 boys. And to get the expected frequency, what we are doing, here you find the corresponding probability. Corresponding probability is at 2 boys. 2 boys. So we need probability of x is equal to 2. Probability of x is equal to, you are finding that is equal to, earlier we have the NCX, that is 4 C2 1 to 1 by 2 power 4, and that is 6 into 1 by 2 power 6 into 1 by 2 power 4. Okay. So what is the expected frequency? Expected frequency of this case, that is expected frequency is n into corresponding probability. Corresponding probability means probability of x. So that is 2000 into probability of this x6 into 1 by 2 power 4. So that means out of 2000 families, how many families have 2 boys, children with 2 boys? That is equal to 2000 into 6 into 1 by 2 power 4, that is equal to 750. So this is the expected frequency. So out of 2000 families, we can expect 750 families have 2 boys. Similarly, you find the expected frequency of the third event. Third event is 1 or 2 girls. Your corresponding probability values you find and multiplied with 2000, you'll get the value. That is probability of x is equal to 1 or 2. That is probability of x is equal to 1 plus probability of x is equal to. That is equal to for C1 plus for C2, 1 by 2 power 4 is common with the expression. So that is 4 plus, that is equal to 6, 1 by 2 power 4. or that is 10 into 1 by 2 power 4. So what is expected frequency? Expected frequency is equal to capital N into probability of x is equal to x. X is equal to x here, that is 2000 into this 10 into 1 by 2 power 4. So that is, suppose you are finding out of 2000 families, how many families have either one or two boys? Children with the four children family you consider, of which one or two boys have the expected frequency is 2000 into 10 into 1 by 2 power 4, that is equal to 1250. So this is the expected frequency. And similarly, the next event is no girls, that is probability of no girls. That is, suppose we have probability of no girls among the children. So that means probability of x is equal to all are boys. X is equal to 4. So that is 4C4, P power 4, Q power minus. So that is 1 by 2 power 4. And so expected frequency is equal to capital N into that probability, that is equal to 2000 into 1 by 2 power 4. So that is among the 2000 families with 4 children, the families with no girls, that is all are boys, you can expect the 125 families. So these are the actually expected frequencies obtained on the basis of the binomial probability mass function. Suppose we have a random experiment, and that random experiment satisfying the conditions of the binomial distribution, that is, it is a Bernoulli sequence of trials with the probability of success P throughout the trials, and X is the number of successes obtained. Of such situation, suppose we want to find expected frequencies, then this is the way in which we are calculating the values. So with this, let me wind up this session, and more problems related with the other distributions, Poisson distributions, and other distributions we will discuss in the next session. So thank you for hearing this session. Thank you.